Okay, so shall we start or should we wait for some more time? I don't think many are going to join. Okay, I think we'll just get started. So there are 8 questions in this exam and multiple subparts. Okay, so yeah, so let's start with this one. You have 4 training experiments in which you train a neural network on the same data set for the same number of epochs. Okay, and you are plotting the loss versus the number of epochs for all 4 models, and you are retaining the model at the 50th epoch in all 4 cases. Then you have to match the following statements, right? So there you have 4 separate statements: bias, variance, 3 statements that involve bias and variance, and 1 statement that has to do with the learning rate used during training. So choose the most appropriate pairing of models with the statements. Okay, so what did you all answer for this? Any answers? What did you all select?
So first one is low bias and low variance.
Okay. One M2. What is
Third
M2?
one is high variance and low bias.
Which one? Which one?
Third one, this M3.
M3. Okay. What is M2?
So it is having high error. So
Okay. So yeah. So M1 is low bias, low variance. M2 is, see, the learning rate used is very high. That is the most likely reason. If your loss is increasing, ideally your loss should decrease as you train the model, right? But if the loss is increasing, then the most likely reason is that the learning rate is high. Okay, so that is M2, and this is M3 is like, looks like high bias, low variance, and M4 is high bias and low. Sorry, M3 is what? High bias, sorry, low bias, high variance, and M4 is high bias and low variance, right? So that is the idea behind the question, but actually there is an error. So I'll look at the results and I'll maybe arrive at a decision. There's a mistake actually in the way this question is asked. So there's a very fundamental mistake, which is that bias and variance, okay, bias and variance are terms you associate uh, with the model, with a particular model class or with a particular class of models. Okay, so we generally don't associate bias and variance with a particular model. Okay, we usually associate them with an entire class of models. So for example, if you, let's say you train a linear regression model and then you train a very deep neural network, then you tend to say that the linear regression model has high bias because it's a very simple model, meaning the class of models which come under the heading linear regression, they have high bias because they are too simple, and the class of models that come under the name deep neural networks, you would say that they have low bias, right? Now you will not use the term bias and variance for a single model that you get out of your training process. Okay, so in that sense, this question is kind of maybe incorrect or possibly incomplete, because what I should have mentioned is the model class corresponding to M1, or rather M1. So the right statement would have been the following, right? So M1 comes from the family of low bias and low variance models. Okay, it is okay to say that the family that M1 belongs to has low bias and low variance. It is kind of incorrect to say that a particular model has low bias or high bias, right? So if you recall in the revision session we discussed, right? So the bias and variance are all expectations. So on an average, if you average over all possible models that you can train on a particular problem, bias is how far it deviates from the true value. So these are all average results, right? They are not on a model to model basis, right? So that is the reason this problem is kind of ill defined. So that is something you'll have to keep in mind. Okay, I've just mentioned this here. We'll see how different students have responded. One thing is kind of correct. So M2, those who have selected M2 learning rate is high, right? That matches with M2. There's no ambiguity there. But in the other three cases, there is a bit of ambiguity. Okay. So I just wanted you to know that bias and variance are for classes of models, not for particular models, right? So please keep that in mind. That is one thing I wanted to say. Okay. Yeah. So that is first. That's the first question. What about this one? Which of the following optimizers use an adaptive learning rate? It's a giveaway. Which are the two? This one, this one, right? So there is nothing much here. So that's a freebie. Okay. Then we have this question on parameter sharing. So an autoencoder is a network in which the input and output have the same number of neurons. That's the main part. So there is one hidden layer in between, and the number of neurons is in the hidden layer is given as a percentage of the number of neurons in the input. Okay, and you will have like two weight matrices, right? One is W1 and another one is W2. So the network will look something like this. So if you think about it, uh, you will have, say, this is this is the input layer. So this is like input layer that has a number of neurons. There is exactly one hidden layer, maybe that's slightly shorter. It has only 30% of the neurons, right? And then you have the output layer, which has the same number of neurons. So that goes here. So the way your weights will now look like as follows, right? So this will be W1, whatever goes from input to first hidden layer, and this one is W2, right? So there are two scenarios. One is W1 and W2 are separate matrices. So in that case, so if you have, let's say, this 30%, yeah, I'll come to that 30% bit. So if you have N1 here, you will have N1 here. Now, let's say you have N2 here, right? N2 neurons. So what is N2 equal to, according to the question? Any answers? Yeah, I already know the answer. So you should tell me what you all wrote.
0.3 N1.
0.3 N1. Okay, so that is according to the question. So do you actually need this 30%? Do you need this 30%, or can it be anything? Can it be 0.5 and will the answer change? Actually, the answer won't change. Okay, so that was this is like just to confuse you. I mean not with a bad intention, but that was not needed actually. So how many neurons? So let's just call that N2. Let's not call it N, some fraction of N1. So the scenario one, right? So scenario one is the weights are not tied, meaning you have two different weight matrices. So in scenario one, what will happen? You'll have N1 into N2 weights. Sorry, yeah, N1 into N2 weights between first layer, the first hidden layer and the input. Okay, and you will have N2 into N1. So no biases. Therefore, this is how it will look like. So you'll have to store these many parameters, right? So these many total number of parameters together is this. Okay, and this is scenario one. Okay, what is going to happen in scenario two where the weights are tied? Can someone tell me what you got? if your weights are tight, meaning W1 is W2 transpose or vice versa. So you'll have N1, N2. That's all, right? Because W2 is W1 transpose. So you really don't have a new set of parameters. So what you have is essentially only W1. Okay, W2 can be obtained from W1. So when you are storing it on a disk, on a hard disk, you only need to store W1, right? Because W2 is just a copy of W1 with the shape, with the matrix transpose, right? So you don't need to store a new set of weights. Okay, so the ratio is therefore 2 n1 n2 by n1 n2. So that's 2. Okay, so the answer is 2. It's actually a very simple problem and nothing much. The main thing we wanted you to take away from this problem is that parameter sharing in the form of weight tying happens in these networks called autoencoders. And when that happens, you're actually saving on not just memory. So this is actually focused on memory, the memory footprint of a network. But it's not just memory that you are saving, it's also structurally you are kind of forcing the network to learn with fewer parameters. Okay, so that's a structural constraint that you're imposing, which is what acts as regularization, right? So we are imposing a structural constraint which ends up regularizing the network. Okay, so that is something you have to take away from this problem. So the next one is again another problem involving regularization. So you have two classes, 5 classes, and the yeah. So you are having 5 classes and you are injecting noise at the output, so that the noisy true label is this one, and your actual predicted label is this. Okay. So what you need to now do is find the cross entropy loss. So to avoid confusion, we have given explicitly the two vectors that you have to use to find the cross entropy loss, right? You should not do it for y and y hat. Instead, you should do it for y noise and y hat. That's the whole point of adding noise. Okay. So what is the loss as a function of y hat and y noise, right? So this will be, what is the formula? Sigma, yeah, I equal to 1 to 5 minus, sorry, this is not y hat, right? There's no hat here. There's just y noise. So should I put y noise here or y hat here? What should I do? Is it y hat or y noise? So this is the true label, right? So it's minus y noise I, okay, minus the predicted label. So minus y log y, okay, sigma minus y log y hat. So what goes in here is the noisy version, and then it's a simple computation. So you just have to do minus 0.9. So that is the first term, minus 0.9 into log 0.6, right, to the base c. So, and then you have 4 terms which are identical. So you have 4 into 0.025 log 0.1. Okay, so this turns out to be, I think, what, 0.64. I don't remember exactly what this
0.69. Yeah.
0.69. Okay, so
Yeah.
this is approximately 0.69. Okay.
Yes.
So again, this is hopefully quite a straightforward problem, right? So the point is, you are adding so this is a soft target, right? Not a hard target. So that's what, there's nothing for you to take away from this question. It's just a straight computational question, so nothing conceptual here. So next we go to phi. So input volume to a CNN, so to some layer of a CNN has this shape, 64 cross 64 cross 8, right? So the spatial extent is 64 cross 64, 8 channels, and you have 16 kernels, each of size 5 cross 5. So stride is 1 and padding is 2. Okay. What you're asked is, what is the shape of the output volume after the convolution operation? Okay, so just give me a minute. I'll make this full screen. Yeah. Okay, so we have to find the shape of the output volume. So what is the, we can translate this into variables that you are familiar with. Okay, so what is Wi? 64, is that correct? Sorry, what is input? Okay, Hi is also 64. What is depth? Di?
8.
8. Okay, that is with regard to the input volume. Now we can ask, what is F? F is
5.
5. What else? S is equal to 1. P is equal to 2. What about the depth of the kernel?
65.
How deep? That
8. 8.
that will also be 8. Yeah.
8.
Okay, so that is the same as this. So that will be 8. Now it's just a question of applying the formula, right? So you could have also done this without using the formula. So one way to see that, so you should have done quite a few questions, right? So whenever you use a 5 cross 5 kernel with padding 2, the input and output will have the same spatial extent. So you can directly say that this has to be 64 cross 64 cross 16. Okay, so there's actually 5-second answer. But then if you have not done that many questions using CNNs, you can always go the proper way, proper route, which is WO is, there's a formula, WI plus
F.
is
F
it
minus
plus?
2p.
Okay, is it plus F or minus F?
Minus F plus
Minus.
2p.
Minus F plus 2P. Okay, by,
S.
yeah, by S
Plus 1.
plus 1. Okay, yeah, so this turns out to be 64 minus 5 plus 4 by 1 plus 1. So 4 minus 5, so it will turn out to be a 64. Okay, so one hint or one useful tip is that for so for same size, okay, how do I put this? For the input, so this is a requirement in many CNNs. So the requirement or something that's useful to have is the input and output volumes tend to have, okay, the same spatial extent. Okay, so you can see what will happen. So if you want a 3 cross 3, if you use a 3 cross 3 kernel, then you'll have to use a stride of 1 that will ensure that you have the same input and output spatial extent. Okay, and if you use 5 cross 5, then that implies you have S equal to 2, sorry, not straight, padding, right? 0 padding. So what padding should you have? This was one of the end term questions last term. Okay, so what is the 0 padding that you should have so that the input and output are the same size? So what do you think P will be if you have 7 cross 7?
3.
3, right? So what you are essentially doing is you are solving this equation. So you take this and then this is like aside, okay? Okay, so this is another question altogether. So you can ask, in general, what should be the padding P so that the input and output volumes have the same spatial extent. So you can solve this equation. So you have W naught equal to, this is the equation that you have. So what should I write here if I want to find out P? I should write something here. W naught WO equal to
W1.
WI, right? Okay, so assuming units, right? Okay, so we make that 1. So we make stride 1. So therefore S is 1, and you can just see that P is equal to, so W0, W1, WI will get cancelled. So you will end up with F minus 1 by 2. Is that correct? So you can now plug this back. So P F minus 1 by 2. So 3 minus 1 by 2 is 1. 5 minus 1 by 2 is 2. 7 minus 1 by 2 is 3, so on, right? So this is a useful result to keep at the back of your mind. Okay, so that's 64 cross 64 cross 16. So 16 is because you're using 16 kernels. And what is the total number of parameters associated with the conv layer? So what is it?
3200.
3200. That's correct. So we have the formula. So you have how many? You have F cross F, right? So you have F cross F. That's the number of parameters for one slice. But then you have how many slices? You have T slices, correct? So that is one kernel. So one kernel itself has F squared D parameters, and then you have K such kernels, right? So this is what? This is 5 square into D is 8, 16. Okay, so this will turn out to be 3200. Finally, if the input volume is changed, right, it becomes 128 cross 128 cross 8. Currently, it is 64 cross 64 cross 8. So what will happen to the number of parameters? What did you all answer?
It will remain the same, yes.
Yeah, it will remain the same. Right? So the number of parameters is independent of the spatial extent of the input volume. One way to see that is to look at the formula, but the other way, so in the formula, notice that W not, so WI does not make an appearance. The only thing that matters is the filters spatial extent, the depth of the input volume, and the number of filters used. Okay, so that is that's a useful result to keep in your mind. Okay, so next problem is you have a toy network or a regression problem. Okay, now there are n layers. N layers, yeah. So there are n layers. So 1, 2, 3, all the way till n. So this is the nth layer. N minus 1 of them are hidden, and the final layer is the output layer. So loss is usual squared error and squared loss. You have a ReLU neuron. Everywhere it's ReLU except the last one, which will be identity. Okay, linear. Okay, linear identity. So what happens if all the weights are equal and equal to some constant k? Find y hat. Okay, so what is the answer? What did you all select? If x equal to 1 and y equal to 0. Okay, so it's actually a very simple problem again. So every single weight is k. So what is going to happen is you have to do a few rounds to see what happens after every layer. So this is this is conveniently 1. Okay, so whatever comes in, it's going to be multiplied by w, and the pre-activation here. So the pre-activation is going to be k, and since k is greater than 0, right, this is an important point. Okay, so if k is, what will happen if k is less than 0? So if you take the same problem and I say k is less than 0,
Then whole will become 0.
yeah, the entire thing will be 0, right? Starting right from the first neuron's activation, you will have 0. So after that, it's pointless because everything else is going to be 0. So k greater than 0 is a must. So in fact, if k is equal to 0, will the answer still be correct or will it be wrong? So k power n is the answer. So is the answer correct for k greater than or equal to 0 or only for k greater than 0?
Only for greater than 0.
Why is it not true for k equal to 0? It is, right? In this case it is. So see, if k is 0, k power n will be 0, right? So it is actually true for k greater than or equal to 0, but the two situations are slightly different. Okay, so yeah, anyway, so that's a trivial point, but anyway. So k power n, I hope you got it. So you multiply this by k. So another weight of k, so k square. So after the ith layer, so the activation after the ith layer is k power I. Okay, I hope that is clear. This is the case because the activation function is ReLU, right? Is ReLU and k greater than 0, right? Both of them contribute. So that is that's the reason it is k power n. I hope there are no other questions here, right? So this is clear
Sir,
enough.
why for k equal to 0 it is also valid, sir? How?
Because k, so you only mentioned, right, it is 0. So y hat is 0 if k equal to 0. K power n is 0 power n, right? So it doesn't matter if k is 0. It won't work if k is negative. So this result uh, is invalid if k is less than 0 the first because the first activation or the activation after the first neuron will be 0. Okay, so for k equal to 0 it is still valid, but anyway that's a minor point. We can ignore that. So this is the slightly hard part. So it's hard in the sense tricky. So there was a deliberate reason why this n minus 1, 2n minus 1, 2n, all these options were added. You have to find the derivative with respect to the first weight. So the weight connecting the input and the first hidden neuron, right? This is just chain rule, but you'll have to be careful to keep track of the exponents, right? So the first is the forward pass, where you notice you have already figured out that the the predicted label is sorry y hat equal to k power n. So this is with you. Now you go for the backward pass. Okay, so what do you do? What's the first step? What will be the first step that you do if you want the partial derivative? Start from the last step, right? So start from the loss. So you have dou L by dou W1 is what you need. Okay. But what I can do is I can first compute dou L by
Why?
sorry,
Why? Do why?
dou L by dou y hat, right? Dou L by dou y hat, and I can multiply this with dou y hat by dou W1. Okay. So that's the first step. So first step, dou L by dou y hat, you must have, even if I wake you up from sleep, you must tell me that this is y hat minus y. You have done that so many times. Okay, so it's just half y hat minus y whole square. If you differentiate, you will get this. And then you are left with dou y hat by dou W1. Okay, now this conveniently, this is k power n because y hat is k power n and y is 0. So you don't have to do any computation there. So you just replace that with k power n. And then you have dou y hat by dou 1, dou W1. So how do you split that? You want, so W1 is all the way down here. What you can do is always remember when you're doing back propagation, the pre-activations, the A guys, right? A1, A2, A3, they are the ones who will always save you, right? So you'll have to first do dou y hat, where are we? Dou y hat by dou A n. Okay, so this we'll copy this here so that it's easier to keep track. So see, this is a1. So what will these quantities be? So you're interested in these quantities. So a1, a2. Always focus on the pre-activations. So they are okay. So when I say a1, it's just before this neuron. Okay, likewise an is just the pre-activation for the output neuron. So how do I split this? I call this dou y hat by dou an into dou y hat by dou an by dou w1. Now this is k power n and dou y hat by dou an. Okay, what is this? Y hat with respect to an. If you differentiate, what will you get? No one did this question?
Sir, 1.
Sorry?
1.
1, right? Yeah, so that will be 1. So see, y hat equal to an because the activation is linear, right? Identity. So that becomes 1 and you're left with dou an by dou w1. So which I can now further break down into an. There is an an minus 1 hiding here. Okay. So that's what. So an minus 1 will hide here. So I can use dou an by dou an minus 1 into this fellow remains, right? Dou n minus 1 by dou w1. Okay. So this is what? K power n into an with respect to an minus 1. There is actually one more step in between. So between an minus 1 and an, there is hn minus 1, right? So what is dou an by dou hn? In fact, let me break this down into hn. I hope I've not lost you, right? This is simple only, right? Yeah. So what is dou an by dou hn minus 1? What is this quantity?
K.
Okay. So go back to the forward pass. We are looking at
One.
wn, right? So see, what is an? It is wn into hn minus 1, right? So dou an by dou hn minus 1. I'm this with respect to this is wn. What links the two? Wn links the two, right? So this is wn. Right? So what is hn minus 1 and an minus 1? Always go back to the forward pass. So an minus 1, or rather hn minus 1 is ReLU of, okay? So what is the derivative of ReLU? You are essentially asking the derivative of ReLU here, right? Yeah, it is 0 if it is less than 0. An minus 1 is less than 0, but thankfully in this case it's all positive. So this will be just 1, okay? The derivative of ReLU, remember, is 1 if it is positive, and it's just 1. And then you're left with this one, right? Dou an minus 1 by, right? So this is what? This is k power n, but wn is itself k. That is given to you. So this is k power n into k into this quantity. Okay. So now what is going to happen is there's a pattern here, and you should quickly figure out this pattern. So when you differentiated with respect to, so when you went, what have you done so far? You have gone one step back. Okay. And you have from an, you have reached an minus 1. So there you consumed one weight. If you go back one more step, you will consume another weight. Okay. So if you keep going back until this step, right? So wherever my cursor is pointing to, you would have consumed n-1 weights. Okay, so this is the catch. So there's a dot business here. Okay, so that's k power n is the output, and then you have done this n-1 times. Okay, and you have reached dou L by what would you have reached if you go all the way till that? Dou something by dou W1. Dou A1 by. Is this clear to everyone so far?
Yes, sir.
Okay, so what is dou A1 by dou W1? What is A1? It is x into W1. Okay, so dou A1 by dou W1 is just
X.
x. Okay, so that's where this becomes 2 power 2n minus 1 into 1. Okay, dou A1 by dou W1 is x. In this case, x is 1. Therefore, you are left with k power 2n minus 1. So I have kind of have written so many steps. You don't have to write all those steps. Okay, you should immediately see that this is y hat minus y into a product of the weights. You are just multiplying the weights. Relu's, all their derivatives will be just 1. So it's just y hat minus y into wn minus 1, so on till w2. When you come to w1, you have to be careful. You can't use w1 again. You'll have to use x. Okay, so that's how the k n minus 1 case come in. K power n plus n minus 1. Okay, so slightly hard. But yeah, so that's this question. Okay, so if wi is not equal to 0 for any of the weights, okay, none of the weights are 0, and if the predicted label is 0, then what can you say about the weights? So y hat is 0. This is a new subproblem, right? So this predicted label is 0, and none of the weights are 0. So what can you conclude? When will your network output a 0 value? Only if
Input is 0, then it will be.
okay, either the input is 0 or you have relu neurons, right? So one of the relu neurons has to not fire. Okay, that's the only case. The input is not 0, input is 1. So the only way your output can be 0 is if one of the relu neurons becomes 0, right? There is no other way, because all the other weights are positive. Sorry, non-zero. Okay, so this can happen. The output can be 0 only if one of the weights, right? One of the relu neurons outputs 0. Okay, if every relu neuron outputs some positive value, see relu. Note that relu neurons can only output positive values, rather non-negative values, right? So if every relu neuron is going to output some positive value, the output is going to be positive. It won't be 0. Okay, so for you to have a 0 output, you need a black sheep somewhere. So some relu neuron has to output 0. Okay, so that means some input to a relu neuron is negative. Okay, but what is an input to a relu neuron? It's just weight into pre-activation. Okay, so at some point, this means at some point, some weight has to be negative. Okay, now you could ask, why should only the weight be negative? Why can't the pre-activation be negative? Can that happen? So for instance, A2 can be negative, right? Why should W2 only be negative?
Because X is positive.
Yeah, because X is positive, right? So you start with a positive pre-activation in some sense, Therefore, at some point, you need to have a negative weight. No other go, right? So that's what this option is like a convoluted way of saying there is some negative weight. Okay, so that's the idea behind sixth one. Sixth one is slightly hard. So we wanted to have some hard question in the exam, and already the first five are kind of easy. There's nothing in this fifth question and all, right? So we wanted to have some hard question. Okay, so this is a regression problem. You have a image, and y is the true label. True label is 4, and you have a simple convolution ReLU operation. One kernel only, no padding. Stride is 1. Okay, find the uh, output produced by the con plus ReLU layer. Okay, it's actually not very hard. So you'll just have to stride this over or move this over the image. So if you go, you will end up with 5334. Do you want me to explain this? It's kind of easy.
He said the confusion in this question was plus ReLU. Sir, that makes it like a bit like where ReLU is applied.
Okay, but it's always applied after the convolution. But even otherwise, right? You must be aware that everything here is non-negative, right? So even if you take out ReLU, that's why we didn't want to. So we were aware of this confusion. You might usually we tend to ignore this ReLU, okay? But actually the ReLU is there. Every convolution is followed by a ReLU. Otherwise, there's no non-linearity in your network, right? So ReLU has to be there. But in this case, it doesn't matter if it is there or it's not there, because all the values are not negative, right? So it shouldn't matter. It's okay, right? What you do, you take dot product. So 0 into 1, 1 into 0. So you'll get a 2 from this row. You'll get a 1 plus 1. So 3 and then plus 2, 5. Okay, so that's how you get 5. I hope this is clear. It's just you'll get 2 cross 2 because you can't stride. Stride is 1, so you can't go beyond one hop. Okay, you'll have to stop at exactly one movement of your kernel. Find y hat. So y hat is just 5 because you have a max pool, and max pool size is given to be didn't we give the size of max pool? Okay, I think we gave. This is an old image that I'm using. Once again, let me just check. What was the size? What was the max pool size? Okay, so in the actual image is different. So I updated this image later on. So f equal to 2, that is given in the question. So this has to be, I updated this and I didn't see update it here. Okay, so it's 2 cross 2. So you will end up with 5. Okay, these are all okay, right? I don't think there's. If you have any question, you can stop me. Otherwise, I'll just go on. Okay, so what is this value? Dou L by dou W13. What did you answer? Anyone remembers what the answer?
I answered 2.
Yeah, 2. Yeah, that's correct. Yeah. So let's see what happens. This is the first thing we need to do is find the derivative with respect to the max pool operation, right? So the max pool operation has you are applying this pooling operation over a kernel of type, over a filter volume that is of size 53. So 5334 are the values, right? Now you apply max pooling and you end up with 5. Okay, so when you are back propagating, this will be replaced by a mask. Okay, so what will the mask be?
Sir, it will be 1000.
Yeah, 1000, right? That will be the mask. Okay, so in case this is not clear, this is you are actually trying to do what you are trying to do. Max of the max pooling is essentially max of four values. Okay, A, B, C, D. So call this A, B, C, D, and in this case it is A. So dou L by dou max pool is will be one for that A value, that entry alone, right? It will be zero for every other case. So this will be like dou L by dou A is one, and dou L by dou say Z is equal to zero for Z equal to BCD. So that's what we call the max pooling mask. So the only thing which matters is this fellow. So now if you go back, the only thing that matters is the first activation that comes out of my convolution operation. So this is the only entry that I care about now, because everything else is going to be irrelevant. Okay. So what contributes to this phi? How do I get this phi? If you write it down, phi is the top left entry, right? Now if you were to actually expand on this, this is the kernel that you have, and what you're asking is how did you get this phi? So you have w11 into this value, right? So let's copy this also. This is x, right? Sorry, let's go here. Okay, so actually w11 into 1 plus w12 into 0 plus w13 into 2, blah blah blah, right? So what you want is dou L, the partial derivative with respect to w13, okay, which is nothing but the input corresponding to w, or what w13 will multiply, that value, that input value is what is the partial derivative. Okay, so in this case it is 2. So what do you get? You get dou L by dou w13 as, if you come from the back, it's a regression problem, right? So it will be y hat minus y first of all, and then y with max pool. So that max pool is just 1. Okay, that's just the pooling mask. And then there's actually a ReLU mask. Okay, there's also a ReLU, remember, that will also be 1 because everything is non-negative. Therefore, the ReLU part is 1. And once you're done with the ReLU part, you'll have to come to the actual convolution part, which is corresponding to this entry. It is this 2. Okay, the input. Okay, so there is a 2 here. And y hat minus y, once again, should be conveniently what? 1. So y is 4, y hat is 5. So 5 minus 4. So you end up with 2. Is this fine with everyone? How we arrived at 2? Okay, so that is the convolution question. Finally, this is a very simple regularization question. You need to calculate two values. One is the optimum weight value without regularization, with regularization. Okay, so find WD star. How will you solve this? You need to find the minimum.
Find derivative.
Yeah, find derivative and set it to 0, right?
Set to 0. Yeah.
Okay, so what will be the derivative in this case? What will you get?
2w1 minus 2.
2w1 minus
2
and
2w2 minus 2.
okay, 2w2 minus 2. Okay, so you set it to 0 and you will end up with
No, 1 1.
1 1, right? So w1 star, w2 star. Okay, there's another way to solve this. Did anyone try use the other way? So there's a way of seeing the solution right away.
You can just put the values in the equation and see which is the minimum.
Okay. So I didn't see that coming, but yeah, you can do that also. What else? I should have asked this as NAT. Okay, so what is the other way? There's one more way. So that is to see that this is nothing but W1 minus 1 whole square plus W2 minus 1 whole square. Okay, you just, if you expand this, you will get this. So these are two positive quantities, not two non-negative quantities. So the smallest value it can take is value this can attain is when W1 and W2 are 1. It is other way, but first is valid. So both are valid. Okay. Now with the regularization, so what will this be? Can do the same thing. So you'll have an extra W. So lambda W. So you will get, what will you get extra here? You'll get a
plus lambda W1 square plus W2 square.
Yeah, so lambda W1 square plus lambda W2 square. So you'll get a lambda, an extra lambda W1, right?
Yeah.
So there's an extra lambda, so that just goes, that just goes in. Okay, you just get this, and this is set to 0 0 once again. So you'll end up with once again symmetric values. So you'll have 2 by 2 plus lambda and 2 by 2 plus lambda. Okay, so for W star to be 0.5 0.5, you need lambda to be 2. Okay, so that's 2. So the final question is interesting. It's just a slight extension of this. You should have made one observation. So is there any value of lambda for which the unregularized one, so this is W star is what? The regularized. So this is the weight vector for the regularized loss. So is there a situation when the regularized weight is bigger than the unregularized weight? Can that happen? That cannot happen, right? So that cannot happen. Why? So this is, let's take a look at this. This is W star. Okay, this is W star, and this is WD star. Okay, the one without regularization, which is 1 comma 1. So you can use algebra. So pure algebra arguments will tell you that this is what the denominator for W1 star, right, or W2 star, both of them, is always greater than the numerator, right, for lambda greater than 0. So that's anyway the case. Therefore, W1 star equal to W2 star will always be less than 1. Okay, it will always be a fraction. So, and what does that mean? That means that this length of W star can never exceed WD star. Okay, so what you have to take away from this question is the following image. So this is actually we have done this in regularization, right? So you have these circles which are typically drawn. So this is x square plus y square. I'm just drawing some circle, and I'm drawing, say, another circle. So 1 comma 1 will be on one of these circles. Okay, remember that. So both these solutions lie on some line. What is the equation of that line? Do you see what the equation of that line is? Both these points are going to lie on the line
Y.
y equal to, yeah, x is equal to y, right? So both of them will lie on this line. So if you actually look at, you can also add this point, right? So let's add 1 comma 1. So 1 comma 1 is, so interestingly, it lies on that circle. Okay, so this is where 1 comma 1 will be. Now 2 by 2 plus lambda, 2 by 2 plus lambda. Let me add 1 point, right? Say 2 by 2 plus 2. I'll just add 0.5, 0.5. And this can be, let's say, 0.5 square. 0.5 square is what? 0.25, 0.25. Okay. So this is how it look like. So this will be W star, the unregularized. So this is the regularized version, right? And this is the unregularized version. So remember that the goal of L2 regularization, or the aim of an L2 regularizer, is to have small weights. Okay, you could have answered this question even without doing this computation, but that would have been a somewhat a guess. Okay, but the idea is this. So the aim of L2 regularizer is to have, or I won't call it an aim, the outcome, right, of having an L2 regularizer is small weights, right? So when you use an L2 regularizer, you notice that the weights come down. So you are actually shrinking the weights, and as lambda increases, what will happen to W star? You see geometrically what will happen? It will get
Big.
big
Smaller.
or small, right? It will get closer and closer to the origin, right? Meaning it will get smaller and smaller. So that's the whole idea. So as lambda tends to infinity, the weights tend to
It's 10 o'clock.
0, 0. Okay. And you should also note that if lambda is equal to 0, meaning no regularization, we recover the original weights, which is 1, 1, right? So what is happening is this is actually lambda equal to 0 case, no regularization. This is, so as lambda increases, this is maybe lambda equal to 2. As lambda increases, this circle becomes smaller and smaller. Okay, so this W star can never be bigger than WD star. Okay, so there is, this question had something to take away, which is that it's a concrete visualization of the effect L2 regularization has on the weight vector. Okay. Okay, so that we have took us 1 hour to answer the paper, and you should have also managed to complete it in 1 hour. Okay, yeah, so that's all I had for today's session. We can meet again on Friday.